So graph in 3 space this equation, 2x plus z equals 4. Okay, we get 30 seconds more. Okay, so let's get grid. X, Y, Z. So this one is in the X, Z plane. I could start out drawing it. There's really an imaginary plus 0y in this, meaning that y can be whatever it wants. It won't affect it. So we're going to draw it in this plane. So if we were in a physical classroom, I'd be pointing to the wall. Like you were sitting here, I'm up at the front of the classroom, and to your left is this wall, and I could be coming over to this wall, and if there was another chalkboard over here, I'd draw on this wall. And what I would draw is this shape. 2x plus z equals 4. Now, one of the easy ways to do this is if the x is 0, the z has to be 4. If the z is 0, the x has to be 2. So if it was in a familiar y equals mx plus b, I could use slope and y-intercept, but I kind of lost that because I'm not in familiar territory here. And then these 2 points, if I connect these, I get a line. And then in 3 space, now the y can be anything it wants. So I go parallel to the y-axis, make this other line parallel to the other blue line over here, and imagine this extended forever. That's the plane that you get here in 3 space. And I'm not, oftentimes on practice quizzes, I won't give you quite enough time to finish, but hopefully enough time to get to a sticking point. And if you get to a sticking point, and then you learn something new, if you can kind of put that in writing, that'll kind of help cement that understanding. Critical component of the learning process is developing this awareness of your own learning, and call it metacognition. So anyway, give me a little feedback on part A. Cameron's got some internet issues tonight, unfortunately. And let's go back to B. Same directions, graph it in 3-space. Now all 3 variables are present. Okay, 30 seconds more. Okay, this one's even easier because there's a technique that works really well here. And that is what we were doing in the table before. Zero out 2 of them. See what the other one's going to be. Zero out these 2. This one's got to be a 4. Zero out the other 2. That one's got to be a 6. And then this is, when it's a linear equation in a space, it's always 1 dimension less than the space you're in. So in 3-space, this is going to be a 2-space plane, and then 3 points are going to determine that, and up 3, and 4 out on the x-axis, and 6 on the y-axis, and then we take these points and we connect them. Imagine this plane going out forever. And we have this. Alright, give me a little feedback on part B. And that, what I'm really fascinated with and keep trying to learn more about is what separates, successful students from unsuccessful students, students who give it a try and drop out of school, or try a technical field and say, oh, I'm not good enough, I can't make it in there. And what seems to be more important than quickness and natural ability is features of how do you react when you first get stuck. Does that prompt you to I have more interest, dig in deeper? Do you stick with things rather than give up soon? Do you, and also another thing called learning strategies. Reflecting on how you're learning, because oftentimes we get stuck in this is my approach, I just read the book. And if it doesn't work, I don't have any other strategy that I can fall back on. And when you get stuck in a certain learning strategy that quits working, can you step back, look at how you're learning and how you've always learned, and say, can I adjust that? Those kind of things seem to make a bigger difference than quickness and what a lot of people call natural intelligence. All right, so let me look at feedback. Okay, and 2, draw and label the vector from the tip of R0 to the tip of R when they're in standard position. Thirty seconds more. From the tip of R0 to the tip of R, the vector has to go in that direction. Okay. If I traveled from the 1 mile marker to the 8 mile marker, my change is destination minus initial position. And so it would be 8 minus 1. If I went from the 8 to the 1, my change would be 1 minus 8, negative 7 instead of positive 7. So we always have to go destination minus initial. We ended up at R. So it's R minus R0 right here. And by the way, it looks this way. If you add the green one to the red one, you add these two together, by the way vector addition works, the R0s would cancel out and you'd be left with R. And that's exactly how it pictures. Alright, a little feedback on number 2. Number 3, give the mathematical definition and the equation of the sphere. So give both a mathematical definition of the sphere and the equation of the sphere with center at 1, 2, 3 and radius of 5. 30 seconds more. Okay, I'm going to draw a quick picture. And I go up 1, go up 2, go up 3, and I have straight up from this point, there's the center. And there's the point, 1, 2, 3. Now, all points that are 5 units away, one such point could be like this, where this distance is 5. Now, we're going to call this point x, y, z. But it's kind of not fair to pick out one point and call it, because this is anywhere that 5 is a distance of 5. All points x, y, z that are 5 units from here, that's the definition. The set of all points 5 units from the point 1, 2, 3. That's the mathematical definition of this circle. And if you put in a plane then you would have not a sphere but a circle. Right. And then, now the equation of this sphere is, this is a fixed point, 2, 3, 1, 2, 3. This could have been chosen anywhere on this sphere. So these are variables, well that's constants. And if we take the distance formula, between this point and this point, we get this. That's the distance between those 2 points, and that has to be 5. Or we could square both sides, get rid of the square root, and have it 25 on this side. Okay, give me a little feedback on number 3, please. Okay. And questions? Questions on homework or anything?
This is Rowan. I have a question
Yes.
kind of about cross products and determinants.
Okay.
Do you know, so kind of what you were teaching us yesterday, or I guess it was Monday, is that the determinant and the cross product are super similar because the determinant can kind of tell you the area of a matrix, and then the cross product tells you the area of the parallelogram of 2 vectors. So do you know which came first? Did the cross product invent the determinant, or did the determinant invent the cross product?
Okay. So in a 2 by 2 matrix, the cross product and the determinant will give you the same answer. But that's only true in 2 by 2 matrix. If it's a 3 by 3 matrix, you can only take the cross product between 2 of the rows or 2 of the columns. You couldn't include the whole matrix in the cross product. coincidental that they turn out to be the same. And, well, not coincidental. They have some relationships that are strong in two space, but that they disperse very different in three space. And as far as which came first, the determinant of the cross product, I'd have no idea. Good question.
Okay, thank you.
You're welcome. Any other questions? All right, we didn't have specific homework last time, so you probably don't have specific homework questions, unless there was something from from way back that you never got totally resolved. Any of those issues? Okay. Yes.
I have, sorry, I have a question about the exam next week.
Yes.
Is it? It's like you show the pages on the screen with the questions written on. Then we look at it and we solve on our paper and scan and upload it.
That's the way that many students will do it. That is correct. Some students, because I generally put lots of space in there, some students who have a printer might want to print it out, and then they have the questions and space in between and stuff, and then they write it all out there and then take pictures of that and upload it. It's your preference.
Oh, so I can print that out and work on it side by side.
You can do it like that.
Mm-hmm. Okay.
You bet.
Thank you.
And you'll have the same amount of time as we have class time. So a week from today, class will start at 5:30. That means the exam becomes available at 5:30. And then the upload, you're available to upload it up until 7:45, but you gotta upload it at or before 7:45. And if you have internet problems, like Cameron has or something like this, and you're trying to upload it right before 7:45 and something screws up and you can't, then you can always email it to me. So don't stress about things like that. But the Canvas page will only accept the upload till 7:45.
Okay, so the question will be the where in this device or Discord or in Canvas?
It'll be in Canvas. So,
in Canvas. Okay, so I can print out. Okay.
If I go into Canvas,
Mm-hmm.
Go into this course, go to modules. When you go to the end of, here, see that says Exam 1?
Yes.
And you'll click on Exam 1, and it says February 17th. And then this will not be available for you right now. I can only see this because I'm in instructor mode here. And then you'll have an upload button over here. And then it's available from February 17th, 5:30 to, actually I made it a little bit longer, all the way up till 8 p.m. So 2.5 hours. And I have this little comment. Soon after the exam started, I'll send a message in Discord to some semi-randomly chosen students stating that we will individually connect for perhaps 10 minutes during the exam. During an individual session, I'll ask the student to do a problem explaining their work. If the student cannot do the problem, I may ask for more problems to be done. Student selection is so I don't choose the same student 3 weeks in a row or something. Okay?
How many questions will be on?
I always get that question, and I never answer it directly because the number of questions is incredibly deceptive. I could, make a test that has 4 questions and it has, A, B, C's and all kinds of things, and I can have tests that have, 30 questions, and it depends on how I break up the material and so on, is how many questions. So I think more in terms of time. And
Okay.
so I think in terms of time is that this is really like an hour and a half exam, but you have 2.5 hours, so you should have extra time.
Okay, thank you.
You're welcome. And the exams, just to run through again the rules, it is not permissible to look things up on the internet. It's not an open book exam or open notes. You can use a non-graphing calculator during the exam. Any questions? Glad you asked about it. It's good to clarify. All right, anything else? All right. Lines and planes in space. 13.5. In 2 space, parametric equations of lines are rarely used because they're bulky and inefficient. That's why you were just taught these. It's the first section, 14.1 of this class, no, 12.1, parametric equations of this class. In 3 space, parametric equations are preferred for both lines and space curves. Now, space curves we're not going to get into today, but since I used the term, let me just tell you what it is. Imagine we've got an x, y, z coordinate system. You can have all kinds of curves in space. You can have, imagine a little miniature alien who's in a little tiny flying saucer. So small that he just occupies one point in space. And he zips around in this curlicue thing, getting further and further away from the origin and making bigger. This is a space curve that he has. And we can map out space curves. And we can come up with the equations of these space curves. And it could be kind of thought of as the flight path of this little bitty alien. But in order to do that, we're going to need parametric equations. Equations of lines, you have 2 choices. They can be expressed as the intersection of 2 planes, because like, you know, the wall and the ceiling in the room that you're in, that meets in a line. So we could define every line as the intersection of 2 planes, but it's much less efficient than using parametric equations. Okay, so parametric equations is just the more efficient choice for equations of lines. And space curves, for complex space curves, I don't think there's any other way other than using parametric equations to come up with the equation of the space curve. Some really symmetric space curves you might get as intersections of some shapes, but most really complex ones, you gotta have parametric equations or you're not going to be able to get the space curve, the equation of it. All right, so we're not dealing with space curves, but we are dealing with these 2 shapes, lines and planes. And we're going to start with a line in 3 space. How do we come up with the equation of a line and so on? All right, we're going to start with the definition of a line. A line is a fixed point P0, which we'll really treat as if it's a vector, plus all multiples of a fixed vector. So for instance, here's the point P, which has these 3 coordinates. Those are constants. Here is a fixed vector, ABC. Now, the line we're going to define is this point plus all multiples of this vector. Now, if we make the multiplier of the vector 1, then we're just simply moving this vector over to here. And we're going to get this point. If we made the multiplier 1/2, we'd be getting this point. If we made the multiplier 2, we'd be getting this point. If we made the multiplier -1, we'd be getting this point. Since we're going to have all multiples of it, we're going to get this entire line. And that's the definition of a line in 3 space. A fixed point plus all multiples of a fixed vector. Any questions? The line L is the set of all points P, x, y, z, such that x, y, z, now this is kind of similar to what we did in the practice quiz. The definition of the sphere was, I just picked one point on the edge of the sphere, but x, y, z could have been anywhere on this sphere. Alright, and then I made what must be true about that, and then this is the equation of the sphere. We're doing something similar here. The parametric equations, line L through P, parallel to V, are yes. So we can have this top one. We can say x, y, and z is x0 plus, now it's this point plus all multiples, the t is the multiplier, of the vector ABC. Now notice how the point P0, I said, which we'll really treat as a vector, and it kind of looks like a point over here, but it could have also, I could have drawn it as a vector, and it would still work. When you take this vector plus this vector, you get a vector going from here to here, but we'd only count the tip point. And then you get all new tip points. And the points that's the tip of the sum of those vectors still maps out the same red line. Okay. And so in equation form, we take that x0, y0, 0, and we turn it into a vector. So it's consistent with the other parts so that it can be all vectors. Since this is a vector, we make everything a vector. But we're going to interpret it such that only the endpoints of the vector are what are important, and it's all got to be in standard position to map out this line in space. So all the points x, y, z that satisfy P0 plus TV make up the line. Now this is equivalent to this parametric equations of the line. Parametric equations of the line, all it is saying, hey, we're going to look at the x-coordinate, the x-coordinate, and the x-coordinate, and make an equation for that. And then we do the same thing with the y's, and we do the same thing with the z's, and we get the 3 parametric equations. So putting it in this format is equivalent to putting it in this format. They're just different ways of saying the same thing. Okay, this is going to take some getting used to, but hopefully it's clear so far. Any questions?
The question.
Yes.
So I can see that at the beginning. Could you scroll up a little bit? Yes. If this is the question is given at the beginning, when you say it's a P is a fixed point,
Yes.
which we really treat as a vector, but how is because a vector a point is a zero vector, or where because it doesn't have any direction. So how do we draw the vector, and how can we even treat it as a vector?
Okay, so if P0 was the point 1, 2, 3, okay, then we can think of the line as the point 1, 2, 3 plus all the different multiples of this vector. It sends us out to all these other, when the multiplier is 1, when the multiplier is 2, when the multiplier is negative 1, and so on. But if we thought of it as a vector, it goes out to the point 1 over, 2 up, 1, 2 on the y-axis, 3 up. We go up to there. And then, as a vector, you can do the normal vector addition, which is tip to tail. So if the multiplier was 1, you'd go up to P plus this one. You'd get a new vector, which would go from the origin all the way up to your end destination. But in this case, we don't think of this vector as a force anymore. We don't think of the P as a force. Right? We just kind of think in a little different way as the tips of those vectors is mapping out places in space. And it kind of reminds me of way back, when I got my first job out of graduate school. I was going to be a teacher right away. This was in 1985. I was going to be a teacher, but I changed my mind at the last minute because I decided I wanted to get a little bit of experience in industry. So I worked at a computer software company called IMSL, International Mathematical and Statistical Libraries. And I had used that software when I was in graduate school. So I was very excited to go and do this. And they had this thing called a plotter. And we had software that would solve differential equations, that would model situations like where they used to have to design a car bumper and then actually build the bumper and then have it crash into a wall at 10 miles an hour and see how much damage it did, and if it did too much damage it was a bad design and then they'd have to go back. Well, they could model all that stuff with differential equations, and they could design it all up, we had the software for it, and then they could simulate this load on it, which was a crash at 10 miles an hour, and then they had this. It was way back in 85, so the tools were rather different then. They had this plotter that would sketch out the graph of the shape of the bumper after the crash. And the plotter was, just imagine a big rectangle, kind of a rectangular with a box that was like 3 inches high coming up from the table. And it had a horizontal arm and a vertical arm. And where those two met, it had a series of pins. And it would drop a pin down, and that pin would drop onto the paper. And then instructions would be fed into the two arms to move them. And so they would move, and it would just push this pin around. And as it pushed the pin around, it mapped out the shape of the bumper after the crash, and so on. And so we kind of are going to view these things, the tips of the vectors, as like the tips of the pen. And then this is going to somehow mark in space, though, the path that we're at. And only when we view it that way do we see then that this maps out a line. So it's a little bit tricky how we shift over from points to vectors and back and forth whenever we want to. But in order to do that, we kind of have to see it that way as pen tips. That we're only interested in the final end pen tip and where does that go. and everything's always in standard position. All right. So the vector v determines the direction of the line. And so now I'm going to have you do a task. Write the parametric equation of the line through the point 1, 6, negative 2 and parallel to 3, 5, 9. And we've kind of had the same group spokesmen for a little while, so let's rotate group spokesman. Hopefully group spokesman is, there's no pressure on it because you can always just report out, what answers you saw in your group chat. And you don't have to necessarily defend your answer or anything like this. And of course, if your group decides to, keep it a spokesman and you have some other reason, just let me know and that's fine too. All right, let me give you a little time to do this. When you get an answer, type it into your group chat, but don't hit enter yet. Okay, go ahead and hit enter. See what others have put in. All right, group 2, what do you have?
We do not have ideas.
No ideas yet?
No ideas yet, no.
Okay. All right, maybe I'm rushing you too much then. Do you need more time or are you a little bit stuck?
So we have a couple of ideas.
Okay.
So, okay, is x equals 1 plus 3t, y equals 6 plus...
This one goes here, and this 3 comes here, and then t. Okay.
And the one said y equals 6 plus 5t.
6 plus 5t. Okay.
And z is minus 2 plus 9t.
Okay.
And some answer will be I put all the three things on the right side of the equation in the vector the bracket.
Okay, if we wrote it in vector form, what would the equation be?
So the 1 plus 3t comma
Okay.
6 plus 5t comma I missed typo, but and minus 2 plus 9t. Was it minus 2 plus 9t.
Okay.
Yeah, that's it.
Great. And we could also be putting a vector equation like this. The vector equation up here says xyz equals the original point oops, it's not working. Plus t times the vector. This equation in vector format means the same thing as this set of three equations right here. It's just breaking them up component by component. Looking at the x components here, the y components, the z components. So these are equivalent. Any questions? Alright, so now we're going to go, that's equations of lines. Going to move quickly and just summarizing. A line is a point plus all multiples of a fixed vector. If we saw it this way, we could kind of see this as, now the negative 2, 1 over 6, negative 2 somewhere down here. There's the 1.1, 2, no, 1, 6, negative 2. And then 3, 5, 9 is 3, 5, 9. It's really mostly up. And then all multiples of this are going to give us then this line, if you took the multiplier to be 1/2 or 2 or 3/4 or whatever, we wind up getting this line in space. And we could also view it as a green vector going from here to here, plus this, and that would give us this other vector, but only the tip of the vector would then be important as it maps out its path in space. Alright, now let's go to planes. And this is something that I really enjoy, but you're really going to have to put your thinking caps on. Determine whether each statement is true or false. And as you're trying to figure out whether the statement is true or false, you might want to be using sheets of paper or the front of a book or something like this as a plane. And you might be taking planes, maybe a couple sheets of paper out, so on. And you might take a pen or a pencil as a line, and you'll be holding these things up in space, trying to figure out whether these statements are true or false. So, first one. Two lines parallel to a third line are parallel. Is that true or false? So first of all, think about it individually. Type up your answer into your group chat, but don't hit enter yet. All right, hit enter. Discuss it briefly. Group 1, is this true or false?
Me and Roman said it's true.
And how'd you come up to that it's true?
I just drew the few lines and compare whether I could parallel, but if both of them are parallel, there's no way it can be parallel to third one.
Right. Now, the problem I would have with drawing lines is I'd be stuck in a certain plane. So instead of drawing lines, I might do something like this. Hold up pins. And I say, all right, these two pins are parallel. And now I take this other one, and it's got to be, so let's say it's all parallel to this one with the red tip. The black is parallel to the one with the red tip. And now this pencil, mechanical pencil, is parallel to the one with the red tip. But no matter how I do it, the black and the blue still have to be parallel to each other. They couldn't be, to be non-parallel, they'd have to, we could think hopefully they'd hit somewhere. You can't make them hit. So yes, I would agree this is true. All right, let's go to the next one. Two lines perpendicular to a third line are parallel. Okay, go ahead and hit enter. Discuss it briefly. Okay, group 2. True or false?
We said it's true.
It's true?
Yeah.
Okay. Well, let me... Here's my first line. These two are both going to be perpendicular to this, and they're parallel. So I seem to agree with you. Unless I can come up with, now no matter how many examples that work, all I need is one example. It's called a counter example that shows that it doesn't work. If I can just come up with one, then I would say it's false. Even though it might be true, it's saying it's always true. So I just need to come up with one. Could I come up with one? And let me do it like this. Have these two, it might be hard to see, but that's perpendicular. This is going to be perpendicular to the pen also, but at a right angle to the other one. And, the red and the pencil, the red one and the pencil, are both perpendicular to the black, but they are not parallel. They could, if I move them together, they could actually intersect with each other. Alright, was that clear? Does everybody follow that?
Yes.
Alright, let's go to the next one. So this one is false. Two planes parallel to a third plane are parallel. Okay, hit enter. Let me come back to group 2 again. True or false?
True.
And if I take 3 sheets of paper, actually I only need to take 2 sheets. If I'm taking 2 sheets of paper, if I put another sheet of paper in between or anywhere else, it can't touch any of those. As long as it's parallel to either one, it's going to be parallel to both. So, yes, that is true. And, alright, we are at a break time.
Rocket ship.
Pardon?
I'm just going to do a steak.
I'm sorry, I didn't mute my microphone.
Oh, okay, gotcha. So, let's take a break. We will start again. At 6:45 p.m. And before I take my break, anybody need to talk to me individually about anything? All right. Okay, let's get started again. And two planes perpendicular to a third plane are parallel. True or false? Go ahead and enter your answer to your group chat. Talk about it for a little bit. Group 1, is this true or false?
We will say, Saron and me say false.
False. All right, now, false is way easier to prove than true, because all you need is one counterexample. Can you describe one counterexample?
It's kind of a tricky, but what I thought was, well, since the plane is the extension of the finite number of lines, so if case of line is false, then case for plane more likely false as well.
Okay, so that's kind of a theoretical construction of it. Can you also can anybody think of an example with like 3 pieces of paper, or the desktop and 2 pieces of paper, that would show that this is false? Or maybe it's true if we can't think of a counterexample.
I have one. If you're looking at the XYZ plane, I guess. If you look at let's say the XZ plane, the XZ plane is going to be perpendicular to the XY plane. And then the plane that we drew for exercise 1 is perpendicular to the XZ plane as well, but it is not parallel to the XY.
So, look at the corner of my room that you can see there. So, the floor and the 2 different walls that make up that corner. Those 3 planes are perpendicular. So we could have the floor, as Rowan is saying, is the XY plane, XY plane. That's perpendicular to each of the other 2 planes, but those other 2 planes are not parallel. And so this was saying 2 planes perpendicular to a third plane are parallel. One more way I could do it is, I'm going to set these sheets of paper with the flat edge on my desk, so they're perpendicular to the desk. And now I'm going to set my second piece of paper. I can make them parallel, but I don't have to make them parallel. As long as one edge is sitting, and so they're perpendicular, there are all kinds of crazy angles to each other. As long as their flat edge at the bottom is sitting on the desk, they are perpendicular to the plane that the desk is in. So this is definitely false. Let's go to the next one. 2 lines parallel to a plane are parallel. Somebody's got their mic open. So check your mic. Okay, type in your answer. Group 2, what do you have for this?
Did you say group 2?
Yes.
I said true, and Matt said false. True. He said true too.
Both of you agreeing true.
Yes.
Okay.
I'm sorry.
Let me. So, my desktop below me, you can't see that, but you can imagine it. That's the plane. And I'm going to make this line and this line both parallel to my desktop. And they are parallel. But do they have to be parallel? This is still parallel to my desktop. Still parallel to my desktop. See, this line, and let me put a sheet of paper instead of the desktop. Here's a sheet of paper. As long as I'm holding this line and that piece of paper are not going to intersect, no matter how I rotate it. So this line is parallel to that plane, and then I can have another line. And these two lines don't have to be parallel. So it's a tricky one. Seems true, but it's false. Starting to get this sense of three space, and what we need is developing some important intuitions here. Alright, and two lines perpendicular to a plane are parallel. Okay, go ahead and hit enter. Group 1, what do you have here?
The Rowan and I said, is it true?
Both saying true.
Yes.
Perpendicular to a plane are parallel. I agree. If my desktop is my plane, then any line perpendicular to that has to go straight up and straight down. And so all straight up, straight down lines are going to be parallel. All right. Now, we have some more of these, which we might come back to at a future time. But that's enough now. Let's go number 5. My goal is, given a specific plane in 3 space, I want to come up with its equation. With equations of lines in 2 space, a single point and a slope was all the information you needed to come up with the equation of the line. Alright, so a point and a slope was all you needed, and you could come up with the equation of the line. In fact, you can put it into the point-slope form of the equation of a line. And voila, you got the equation. We will determine the necessary ingredients of the equation of a plane. Maybe it's 2 pieces of information, maybe it's more. So, I have these 2 important questions. Does the following describe a unique plane? You can use a piece of paper as a plane, a pen as a vector. Each of these 2 situations, does it describe a unique, a single plane? A, one point in the plane and a vector parallel to the plane. B, one point in the plane and a vector perpendicular to the plane. Let me give you a minute to process that individually. All right, so this first one, a point in the plane and a vector parallel to the plane. Let me go to my camera. So let's say my point is right here, and the vector parallel to the plane is right here. So where I'm grabbing the pen is the point, and then the pen itself is the vector. Now, does that describe a unique plane? Well, I can have a plane that goes through that, but I can cock that plane at an infinite number of different angles. And this plane has to contain this line, but there's an infinite number of planes that can do it. So the answer is no. It does not determine a unique plane. We want so that there's no other plane that could be done with the system. Just like a single point and a slope gives you a unique line, there's no other line, just one line with this point and this slope. We want the conditions for a plane, and that doesn't give you a unique plane. We can rotate the plane. Now the plane that has to contain the point and it has to contain the vector that emanates from the point. Emanating from the point. That plane can be rotated in an infinite number of directions. All right. The next one. Does one point in the plane and a vector perpendicular, which we call normal, to the plane, does that give you a unique plane, that there's only one plane that will meet this condition? And we go to my camera. So here's the point in space. And here is the vector. There. in fact, is only one plane that will do this, that goes through the point and is perpendicular. If I rotate it in any angle, it's no longer perpendicular to the vector. It's got to go through this point, but you can't be tilting it any other angle. There's just one plane that does it. Yes. There's just one plane that will do this. All right. This is a pretty important aspect. These two questions and their answers. Go into Discord. Give me a little feedback. Are you comfortable with A and B? Give me something about your comfort level with it. Confusing, but you got it. Might have to go over it again, maybe. Yeah, it's a pretty complex question. All right. Is there a unique plane that this describes? This one doesn't describe a unique plane. This one does describe a unique plane. And well, let's review the conditions that describe a unique plane. It's very similar to a single point and a slope is all you need to come up with the equation of a line in 2 space. In 3 space, a point and a vector perpendicular to the plane is the minimal amount of information that describes a unique plane. With that information, we could come up with the equation of a plane. Just like here, we can come up with the equation of a line if we have a point and a slope. All right. The general equation of a plane in 3 space. A plane passing through the point P sub 0. Now, just like we did before with a line, the point can also be thought of as a vector with non-zero normal vector n. So remember, with a line, we had a vector v that was ABC. But that wasn't normal or orthogonal. That was the direction the line was going in. This one, this vector n, which is we still call ABC, is perpendicular to the plane. So non-zero normal vector means it's a vector perpendicular to the plane. Consists of the set of all points x, y, z. Now the points x, y, z can also be thought of as the vector emanating from the origin that goes from 0, 0 to x, y, z, which we'll call r. That satisfy the dot product of n and r minus r0 is 0, because any vector in the plane is perpendicular to n, and then it has these other variations of this formula. Now, let me describe the visual of this n dot r minus r0, because that's what can give you the intuitive understanding here. Let's come down here. Okay. So, a point in the plane, so the point is P0, which is x0, y0, z0, or r0, And so R0 is this one. That's the fixed point. The plane has to go through that point. And it has to be perpendicular to N, which is ABC. All right, now, I haven't drawn the N in here. I'm just saying remember, and I picked this R0 and this R because way back in the practice quiz, we had the same R0 and R. And we had said, oh, the line between these two, the vector between these two, coming from R0 to R is called R minus R0. Okay, so, going back to that same picture, what I'm going to say is, we have a point. From this point, suppose we have the vector n. Suppose n is like this. Which has coordinates a, b, c. Alright. So I need the plane that contains this point, the tip of R0, and is perpendicular to this vector. Now, if I take the set of all points such that when I make, let's go gray. The plane that I'm interested in is going to be the plane that contains all of this stuff. And it's going to also contain this vector. Now this plane is really a very big plane. And this little vector is a line in that plane. It's also a vector in that plane, part of a line in that plane. So if this was a sheet of paper with the gray boundary, that plane, then this would be a line or a vector on that paper. And this, and the red line comes off the paper. And it's straight up from the paper, so it's perpendicular to that plane, the plane of the paper. Now, this R, remember, it goes from the tip of R0 to the tip of R. Take the destination minus the source. This is R minus R0. This key point here this is a vector in the plane. What was R? R is a point in the plane. Just like, we come way back to practice quiz problem number 3, definition of the sphere. This x, y, z seemed like a particular point, but it really could have been any point that was 5 units away, any point on the sphere. All such points x, y, z that satisfy this equation will be points on this sphere. Same sort of thing is happening here. This R looks like a particular point, but it could have been any point on this plane, as long as it was in the plane. And the set of all points in the plane is really what R is. So that when you take R minus R0, you are going to get a vector in the plane, R minus R0. It's a vector in the plane. N is the vector that's perpendicular to the plane, because it's the normal vector to the plane. So this and this are orthogonal. They make a 90-degree angle. Now, the dot product, recall, is a measure of how much these two things point in the same direction. And they don't point in the same direction at all. This minimizes the dot product, which is 0. So n dot r minus r0 from this diagram has to be 0. They are perpendicular. So the plane, equation of the plane needs two things. It needs a point in the plane, which is R0. It also needs a orthogonal vector to the plane. And then all points in the plane is R, or XYZ, such that when you subtract R and R0, which gives you a vector in the plane, if you dot product that with the normal vector for the plane, you have to get 0. Now then, if you replace n with ABC, replace R minus R0 with XYZ and X0, Y0, Z0, you get this dot product is 0. But when you dot product, you take this times this, plus this times this, plus this times this, and it's got to give you 0. Or, one other way to think of it, and this last one I don't really use very often, but if you distributed and got rid of the parentheses, you'd get an AX and a BY and a CZ. And then the other stuff would all be constants. AX0 plus BY0 plus CZ0. And you'd move them to the other side, and we could say that this is kind of, you get to where we say the kind of the general equation of a plane is something times x plus something times y plus something times z equals a constant. So this is kind of like the standard form that we eventually often put the equation of a plane into. And it looks like this. Alright, so that was a lot. There were lots of places you could have got lost. So, tell me how you're hanging. Does this make sense? Give me a little feedback in Discord. Okay, why do we use the dot product? Why didn't we use the cross product? We could have picked something else. Can anybody tell me why did it use the dot product?
It's like a really easy way to tell if two vectors are perpendicular.
That's right. The cross product, we could have done that. But then we'd have said, oh, the cross product's got to maximize. So then you'd say, all right, the magnitude of the first vector and the magnitude of the second vector. Does the cross product the magnitude of the cross product give you the same as the magnitude of these individual elements multiplied together, and it maximizes. So it's just for convenience sake that we pick the dot product, because the dot product has to be 0. Two things are perpendicular, and these two things are going to be perpendicular. Any vector in the plane and the normal vector to the plane, we decided up here that determines a unique vector. A point in the plane and a vector perpendicular, normal to the plane. That determines a unique plane. And that plane, we can also use the fact that they're normal because their dot product is 0. Remember, the dot product is the magnitude of the first, magnitude of the second, times the cosine. And the cosine of the angle between them is a measure of how much these two things go in the same direction. And if they are perpendicular, the cosine is 0, just like the perpendicular of the cosine of a 90-degree angle is 0. Matt, does that answer your question?
Yeah, that completely makes sense now.
Okay, good question. All right, let's move on. Find the equation of the plane through the point 5, 2, 4, perpendicular to the vector 3, 2, 1. And let me shrink a little bit so you can kind of see the picture. Let me give you a minute. Transfer that question up to here. So you can see the question and the formulas in the same view. Okay, so this is the R0. This is the normal vector. And so we could write the equations of the plane in this form, we've got all these different forms that we could use. One format that I kind of like is this very first one. N dot R minus R0 in vector form is 0. Now sometimes the answer we have to put like a vector above this, because sometimes that's a 0 vector. And if we were doing cross products, we would have had to put that, because the cross product of two vectors is another vector. But the dot product of two vectors is a scalar, so it's not the 0 vector. So this is going to become 3, 2, 1, dot. Now R, over here, it's X, it's any point in the entire plane. satisfies this condition. That when you dot product, when you take this minus R0, and R0 is 5, 2, 4. So we're going to get x minus 5, y minus 2, z minus 4. That's that vector. We got to get 0. Then when you dot product them together, you got 3x minus 5 plus 2y minus 2 plus 1 z minus 4 equals 0. Now you can clean this up a little bit. For me, I'm okay if you leave it like this. Equation of a plane, you can leave it just like that and totally be fine. If you're going to check your answer in the back of the book, you're probably going to have to multiply these out and then move the constant over to the right to see if it matches up, because the answer to the back of the book will probably use this last format. Any questions?
I have a question. So when you asked us whether it's so why this is not a cross product and it is a dot product, I was just thinking, and actually you draw the plane here, right?
Yeah.
So dot product is always on the plane, but a cross product, the result of the dot product will be on the same plane. But the result of a cross product involves a different third dimension, correct?
You're sort of correct.
Right?
You got
So
something right and something not right. When you dot product two vectors, you don't get something on the plane because the dot product of two vectors is a scalar. It's no longer a vector.
So it only regards to two dimensions, but cross product always involves a third dimension. Is that why?
And the cross product
finding-
of two vectors is always a vector, and it's perpendicular to each of the other two vectors.
Right. So you need another dimension.
That's okay. But in 3 space, yeah, we could put two. So these are 3 space vectors. N is a 3 space vector. R minus R0 is a 3 space vector. If we cross product them, we'd get another 3 space vector that'd be perpendicular to both of those. But it wouldn't be useful to us. It wouldn't give us something that would allow us to get the equation of this plane. We get the very simple equation of the plane if we dot product these two and then say the scalar result has to be 0 because we know these two things are perpendicular. Does that clarify it a bit?
Yes.
Okay.
That's fine. Thank you.
All right. Anything else? Any other questions? All right. Find the equation of the plane through that point. Well, we just did that. What is the minimum number of points to determine a unique, remember, one and only, I already had this unique idea before, a unique line and a unique plane. So get an answer for each of these and type it into your group chat, but don't hit enter quite yet. All right, go ahead and hit enter. So group 2, what do you have for A?
So I got 2 points for a line and 1 point for a plane.
Okay. So I agree with you in two space. If I have 2 points, that determines a unique line.
Although actually, wait, would it be 3 points for a plane?
Why 3?
Well, I was just thinking of how we talked about earlier, how we could draw the 3 different points from the equation, and from those 3 points we could create the
Yes,
plane.
you're exactly right. If I had 2 points here and here, I could put a sheet of paper that contains these two, but I could rotate that sheet of paper in all kinds of different rotations. And so that doesn't determine a unique plane. But if I have a third point, then there's really only one plane, and I can actually visualize it by just connecting these points. There is that plane. Just imagine this going out forever. And we were doing that with intercepts, x and y intercepts, before to draw them as well. So you need 3 points to determine a unique plane. Okay. So number 9 is find the equation of the plane through these 3 points. And this is a tough problem.
Whoa.
And I think somebody's got their microphone open. So check your mic.
That was me. I actually got kicked out, and then something happened to my audio, so I just missed like 5 minutes. But I'm gonna be quiet now.
Okay. All right. Sorry about it. Isn't that a pain in the ass when you get kicked out and have internet issues and all that stuff? All right. So we got 3 points. We need to come up with the equation of the plane. Let me give everybody a minute to think about how you might do this, and then I'm going to ask for a strategy, and then we'll kind of do it together. All right? But we'll start by just giving everybody some time to process. What in the world is this asking, and how might I go about this? So, take a minute on your own first. All right. So before we get started, what 2 pieces of information would be really nice to have to make the equation of the plane? That's my goal, to get the equation of the plane. I'm going to need what? Anybody?
When we talked about earlier how you need a point and a vector that's perpendicular to the plane.
Point and a vector perpendicular to the plane. Now, we have 3 candidates for the point. And it doesn't matter which of these. I'm going to actually select this one though. Could have selected any of the 3. I'll select that. That's my point. Now I need a vector perpendicular to the plane. how in the world am I going to get this? A vector perpendicular to the plane. Anybody have any ideas?
You could just take the cross product of two vectors, and like it doesn't really matter what the magnitude is, but the vector that's like when you take the determinant would be perpendicular.
Take the cross products. Take the cross product of two vectors. And where should these two vectors be? In the plane. They gotta be vectors in the plane that we're trying to find. And then when you take the cross products of two vectors in the plane, remember the cross product is a third vector that is perpendicular to both of these other vectors. And since it's perpendicular to both of those vectors in the plane, it will be perpendicular to the entire plane. Everybody follow it? Any questions? All right, so we now need two vectors in the plane. Well, let's call them A and B. Anybody have an idea how I can get a vector A that's in the plane?
I think you can get at the random. I will choose from the 135 to 0.291 and get the vector.
All right, we'll go from here to here. So, what is the vector that goes from 135 to 259?
The vector 16 minus 4.
Perfect. Remember, you have to take destination minus the start point.
Right, and then
Minus 1, 9 minus 3, 1 minus 5. Okay, and B?
from the 135 to 741. 7 minus 1, minus 4 and 1. 3, sorry.
All right, so I'm going to choose between these 2 points here. So that'll be my point in the plane that I'm going to use, and I'm going to emanate 2 vectors out from it, or that include it, and it doesn't really matter, as long as they're in the plane. So we'll go from to, and so then this is going to be, and you always take destination minus where you started. 7 minus 2 is 5. Negative 4 minus 9 is negative 13. 3 minus 1 is 2. Alright, so my vector n is going to be these 2 vectors in the plane cross product each other. Really interesting how we learned about dot product, we learned about cross product, we learned all these properties about it, but then we really need all these because we needed the dot product to get the equation of the vector, or the equation of the plane. That's back up here. It's the definition of how we define a plane mathematically, equation of the plane. And now we need the cross product, in this case, to come up with the vector perpendicular to the plane. So we're going to do this, Now, I'm going to mentally cross out these two, and then I'm going to do this computation. 12 minus 4 times 13 is 52. So I'm just going to save myself a little time here. Minus J, and then I'm going to mentally cross out this row and this column. I'm going to do this 2 minus a negative is plus 20 plus K. Mentally cross these out. I'm going to get negative 13 minus 30. So N change its format. This is going to be negative 40. It's going to be negative 22. It's going to be negative 43. Everybody okay with this so far? Any questions? Alright, and then my point, let's go back up to the general equation of a plane. We called it R0. That's the point in the plane. R0 we make a vector out of that point, and we said it was 291. And the equation of the plane is n dot r minus r0 equals the scalar 0. So it's going to be R, remember, was any point in the plane, but we're writing it as a vector. So it's x minus x0. R0 is right here. But this x0 is really 2. The y0 is 9. And z0 is 1. Now we dot product it all together. Now I'm going to do a trick. I'm going to multiply both sides by negative 1. Because all these negatives could be turned into positives. And I'll get 40 minus 2 plus 22 y minus 9 plus 43 z minus 1 is equal to 0. There is my equation of the plane right here. And I'm satisfied with it being in this format. Don't have to multiply it out, put the constant to the other side. And we are done. The homework. Is 13.5. And the exam next week goes up through 13.5. On Monday, we will cover 14.1. but 14.1 is not on the exam because you won't have had time to ask questions and get everything clarified about 14.1. All right, we'll stop here. I'll stop the recording.
Would you have a spot check?